right, let's practice a little bit more with finding the derivative using our derivative rules, our product rule, quotient rule, chain rule, all the basic rules. Let's see. Let's start with those. So this first one, x times e to the x, that's a clear product. If you want, you can put parentheses around these, but it's certainly not necessary. So f prime of x equals first times the derivative of the second, derivative of e to the x is e to the x, plus the derivative of the first, which is 1, derivative of x is 1, times the second exactly as it is. And you can leave your answer like that, or since we have two terms here, each one with an e to the x in them, you could certainly factor that out if you think that looks nicer, if that's easier to work with. Even with an x in the first term and a 1 in the second term. If you were going to have to take the derivative again, it might be easier to do in this form. And of course, we wrote f prime equals, because this is not the same function as f. That's a completely different function. Okay, give b a shot. This shouldn't take too long. This function that I gave you right here is assembled via composition. We have an inside part. First thing that happens to x is it's multiplied by 3, and then you take e to it. So we have a function assembled by composition. Our derivative, we're going to need the chain rule. So g prime of x, let's do the outside first. The derivative of e to the something, derivative of e to the whatever is e to the whatever. And now at the very end of the problem, you have to multiply by the derivative of the inside part. The derivative of 3x is 3. Derivative of 5x would be 5. Derivative of, negative 50x would be negative 50. And you could leave your answer like that, but I'm used to seeing the numbers out in front. So I'd probably write this as 3e to the 3x. Chain rule. We're going to need a chain rule a lot in the next few sections. And in part C, before you get started, since we don't know a rule for secant, it would probably help to write this as 1 over cosine. That's what secant is. It's 1 over cosine. And so if you want to write it like this, you could use the quotient rule on it. But you have another option. 1 over cosine is the same as cosine of x to the power minus 1. It's the same as cosine of x all to the power minus 1. And if you do it like that, you can use the chain rule on it. Either way, you're going to get the same answer. I'll just let you do whatever you think is easier. We can try them both when we work it out on the board, but give it a shot in whichever way you think will be easier. So if we're going to take the derivative of secant, which is basically 1 over cos, let's try doing it by the quotient rule. Since we've written it like a fraction here, so derivative of the top is just going to be 0 times the bottom, which is really, who cares at this point because it's multiplied by 0, minus the top, which is 1, times the derivative of the bottom. Derivative of cos is negative sine, all over the bottom squared. So that's just 0. And these two minus signs cancel out. So we have sine over sine x. Oops, I forgot my x. That was silly of me. Sine x over cos squared x. So there it is using the quotient rule. Let's try it. Having written it like this, let's try using the chain rule. So to do this, we're going to bring the minus 1 out front. We write the inside exactly as it is because we're not taking the derivative of the inside part yet. It's too early. The minus 1 becomes a minus 2. And then you multiply by the derivative of the inside part. The derivative of cos x is minus sine. And I suppose that minus sign and that minus sign cancel out. So I have, let me write the sign first for no particular reason. I get that. Now, I just did the same problem 2 different ways. These two had better be the same answer, and you can see that they are. Cos x, the minus 2, is the same as 1 over cos x all squared. And so this is really sine x over cos x all squared. Simply the same answer. This is a perfectly acceptable form to write it. This is a perfectly acceptable form to write it. This, they're all fine. I don't know which one looks easier or nicer to you. Let's do a couple more. How about we have f of x equals log base 2 of x. And g of x equals, how about natural log of b to the x. I'm going to give you a hand with D because, well, let me let you think about it for a few seconds. Anybody have an inspiration? I didn't give you a rule for log base 2 of anything, but back in our review of pre-calculus, we studied the change of basis rule. So this is really equal to a fraction. We could write this as a fraction. Remember, if we were going to try to put this into our calculator, log base 2 of some number, we'd have to use the change of basis rule, depending on what buttons you have on your calculator. But I'm going to write this as the natural log of x divided by the natural log of 2. I haven't done any calculus. That's why I didn't write f prime. This is still f. All I did is use the change of basis rule to change it from base 2 to base e. Now I know how to take the derivative of natural log of x. It might look to you like I'm supposed to use the quotient rule on this, but I'm not, because natural log of 2 is just a number. It's a number like pi or 5. So let's just write it as 1 over the natural log of 2 times the natural log of x. These two are clearly, this and this are clearly the same. Natural log of x times 1 over natural log of 2 gives me natural log of x divided by the natural log of 2. And in spite of the fact that this looks like a complicated mess, that's just a number. There's no x's in there at all. That's just a number in front of natural log of x. Just like if we had written 3 in front of the natural log of x. It's just a number. So when you take the derivative of a function with a number out in front of it, you just leave the number there and it multiplies against whatever you get. So we haven't done any calculus yet, which is why I haven't written f prime. I've just keep massaging this into a form where it's going to be easy for me to take the derivative. And now I'm ready. So derivative of natural log of x we know is 1 over x. And the 1 over natural log of 2 just hangs out in front, just like the number 3 would. It's just a number. Don't let scary looking constants make you do things that you wouldn't otherwise with easy looking constants. If you want to type this into your calculator and get a decimal value, that's totally fine. So if you want to think of it as a rule, you could think that the derivative of log base a of x is going to be 1 over the natural log of a times 1 over x. If you want to think of this as a separate rule, you're certainly welcome to. But we worked it out ourselves. And one more before we move on to the next section. Here we have a clear inside part and an outside part. Excellent practice for the chain rule. So remember the chain rule says take the derivative of the outside part first, leaving the inside part exactly as it is, then multiply by the derivative of the inside part. So derivative of natural log of something is 1 over that something. So what I often see as a mistake is people think that this says natural log of x. It's natural log of e to the x. So we don't want an x on the bottom. We want an e to the x. Derivative of natural log of whatever this is going to be 1 over whatever that is. So that's the first part. We've taken the derivative of the outside part, and now we multiply by the derivative of the inside part. Derivative of e to the x is e to the x. And obviously what we've written here is e to the x divided by e to the x, which is the number 1. Now, there was actually a shortcut here. Did anybody spot it? Did anybody do a little bit of algebra before they took the derivative? What's natural log of e to the x? Remember, natural log and e to the x are inverses of one another. So natural log of e to the x is just a fancy way of writing x. The original function was basically x, and so it's not surprising that the derivative should be 1. You know the derivative of x is 1. So let me give you a moment to make sure that you've got everything copied down, because I want to clear the board to start the next section. As I said, the next 2 sections are heavily dependent on the chain rule. Oh, good. The next section is called implicit differentiation. So if we're given a relationship between x and y, say, where y is isolated by itself. Y is by itself on one side of the equal sign, and there are no y's on the other side. We say that y is given explicitly as a function of x. So for instance, let's say y equals x squared minus 5x plus 7. So if we want to find y prime or dy dx, there's 2 ways of writing the same thing, we know exactly how to do it. The derivative of y is going to be, let's take the derivative of the right-hand side. 2x minus 5 times 1 plus 0. Just take the derivative the same way we've been taking the derivative for the past few sections. Use all our derivative rules. So if y is given explicitly as a function of x, so y is by itself on one side of the equal sign and there are no y's on the other, we know exactly how to take the derivative. If X and Y are sort of all mixed together. Not a very technical way of writing it, but I think it's pretty clear. We say that Y is given implicitly as a function of X. So sort of an explicit definition versus an implicit definition. So for instance, let's say we have x squared plus y squared equals 25. Now, what we have there, of course, is a circle of radius 5, centered at the origin. And you already know that that's technically not a function. Y is technically not a function of x. But in certain circumstances, we could restrict the domain and the range so that y becomes a function of x. Well, I'm not going to worry too much about that now. But you can see that the x and the y are together on one side of the equation. So if you hope to find the derivative, y prime or dy dx, however you want to write it, so if we hope to find y prime or dy dx, depending on how we want to write it, the derivative of y is a function of x, we have two options. First, we could try to get y by itself. Isolate y, write it as an explicit definition. In this case, it's not that hard. So we'll just start off with x squared plus y squared equals 25. We'll bring the x squared on the right-hand side, so y squared equals 25 minus x squared. Subtracting x squared from both sides. And we'll take the square root of both sides. So y equals plus the square root of 25 minus x squared, and y equals minus the square root of 25 minus x squared. By the way, this is just the circle of radius 5 centered at the origin. Then this is just the top half of the circle. Y equals plus the square root of 25 minus x squared. And this is the bottom half of the circle. Y equals minus the square root of 25 minus x squared. And once we have it written like this, we can take the derivative using our derivative rules. Let's actually, I'm not going to do both of them. Let's just do this one as practice, because it's a nice application of the chain. So find derivative. Doesn't matter if you write dy dx or y prime. or y equals square root of 25 minus x squared. Before you even start working on that by taking the derivative, before you start doing any calculus, we're going to have to write that square root symbol as power 1/2. So 25 minus x squared to the power 1/2. Haven't done any calculus, just rewritten it by algebra, which is why I can just write equals. I don't have to write y prime or dy dx equals. But now it's written in a form where I can easily take the derivative. We have an outside part and an inside part. This is a poster child for the chain rule. We're going to take the derivative of the outside part first. That 1/2 comes down. 1/2 minus 1 is minus 1/2. And you ask yourself, what goes in here? And you resist the urge to take the derivative of the inside part. We know that's too early. No, it's too early to take the derivative of the inside part. Instead, you write the inside part exactly as it is. All we've done is taken the derivative of the outside part. We're, halfway through, more than halfway through, I don't know. And now we'll multiply at the very end by the derivative of the inside part. Derivative of 25 is 0. Derivative of minus x squared is minus 2x. You're welcome to leave the answer like that. I think there's a little bit of simplification we can do here. I'm going to cancel that 2 on the bottom with this 2. And I'm going to write this to the power minus 1/2 as 1 over the square root. Raise this up to the power minus 1/2 is 1 over the 1/2. In other words, 1 over the square root, 25 minus x squared. What I have here after I've canceled this 2 on the bottom with this 2 on the top is just a minus x. And I can write this as minus x over the square root. 25 minus x squared. There we go. I mean, nice application of the chain rule. So if you can get y all by itself, you can just go ahead and use your regular old derivative rules.
I have a question.
Absolutely.
Because will we have to rationalize the denominator?
Oh, no, not for me. I don't think rationalizing the denominator makes it look any better. I know, and we all had teachers in high school and maybe middle school that made us rationalize every single denominator. I did. And so, when I see something like 1 over root 3, I still have the urge to multiply the top and the bottom by root 3, which just gives you root 3 over 3, because I was told to rationalize every denominator. But I'm not going to make you do that. I don't actually see the point. I know, even though I feel the urge to do it, that's my issue. You don't have to if you don't want to. And I don't think it adds anything to this. I think this looks best without rationalize the denominator. If you rationalize the denominator, what you end up with is minus x times the square root of 25 minus x squared all over 25 minus x squared. I don't think that looks better. I think that looks worse. So when it comes to simplifying, your number one reason to simplify is to make your life easier. There's a certain, if aesthetics are telling you, yeah, I really have to simplify this, it looks much better this way, even though it's not necessarily going to help me, go ahead. There's a certain aesthetic component to this. But here, I don't even think of this as simplification. I just think of this as doing something for no reason. I don't know. I don't know why one would do that. So no, it's a great question, but no. Anyway, back to the story. So if X and Y are sort of all stirred together on one side of the equal sign or on both sides of the equal sign, you could try to get Y by itself. But isolating Y could be difficult or impossible. We were able to do it in this case, no problem. Let me give you another example. Let's say we have x cubed plus x squared y plus xy squared plus y cubed equals, oh, let's say 15. It is possible to get y by itself here. And when I say getting y by itself, I don't just mean y equals and then the stuff on the other side has both x's and y's in it. That doesn't count. So, I mean, I could just, move this onto one side. So like x squared y, and then move all the other stuff on the other side, minus x cubed minus xy squared plus y cubed. Minus y cubed plus 15. All I've done is subtract that term and that term and that term from both sides, and I've just left this one term on this side. I guess I could divide both sides by x squared there and end up with y equals minus x cubed minus xy squared minus y cubed plus 15 all over x squared. And I could say to myself, oh, I got y by itself, but I didn't really, because there's plenty more y's over here. So this doesn't count. So I'm not even going to write that. So you don't have to copy this down. Yeah, I mean, if you really want to, you can play the video back. But that didn't serve any purpose. Getting y by itself here, I'll tell you right now, algebraically speaking, it is doable. But I don't think anybody's going to want to do it. I'm not even sure, based on what you've studied in algebra so far in school, you would know what to do right away, because it depends on something called the cubic formula, which I'm not going to get into. But if you're interested, you can go look it up. You can just Google cubic formula. But anyway, it's way more trouble than it's worth. So as I said, isolating y, getting y by itself, writing this as y equals, and then what's on the other side only involves x's and numbers, no y's. That can be difficult or impossible. In this case, it's difficult. I could write some down that were completely impossible. So our second option, rather than isolating y, so instead of isolating y, we could do what's called implicit differentiation. So the idea of implicit differentiation, you just leave everything where it is. You don't try to get y by itself. You take the derivative of both sides. So in other words, you take the derivative of both sides. treating y as if it were a function of x. So whenever you hit a y, so the derivative of y whenever you hit it, when you're taking the derivative of everything on both sides, you just write down y prime or dy dx. And I'll explain this process. I'll start with the first example rather than the second example, because this one's going to take a bit of work. So let's go back to our first example. The x squared plus y squared equals 25. We are going to take the derivative of both sides. We write this expression, take the derivative of both sides, so often that the best thing to do is just abbreviate it. You write TDBS, which is just take the derivative of both sides, and with respect to our independent variable x. So TDBS, and then I just usually put x in quotes. Take the derivative of both sides with respect to the independent variable x. So x is just a regular variable, but y is going to be a function of x. So this time, instead of getting y by itself, we're just going to leave everything where it is and go through from the left to the right and take the derivative of everything. Most of this is easy. We start off with x squared. The derivative of x squared is just 2x, the same as it always is. Now we come to that y squared. It's hard to see, but what you have here is a composition. You have an outside function, which is something squared, and an inside function, which is just y, because we said y is a function of x. So the derivative of y squared is not going to be 2y, because we're not taking the derivative with respect to y. We're taking the derivative with respect to x. That's our independent variable. So we have to use the chain rule on this. Chain rule says the 2 comes down. You write your inside exactly as it is. Those parentheses don't really matter. I'm just putting them there to make this clear as to what's going on. You write the inside exactly as it is. Derivative, the 2 comes down, you write the inside exactly as it is. The 2 becomes a 1, which I'm not going to write. And then at the very end, you multiply by the derivative of the inside part. The derivative of y is dy dx, or y prime. I'm going to write dy dx right now. I use the chain rule on y squared. When you're sort of just going through this process quickly, a lot of people just think, okay, every time I hit something with a y in it, I'll just take the derivative normally. Derivative of y squared would be 2y, and then I'll put in a dy dx. Every time I hit something with a y in it, I'll just remember to put in the dy dx, and that's fine. But it just comes from the chain rule. Equals derivative of 25, just a number. Derivative of 25 is 0, because derivative of any constant is 0. So now I have 2 terms, 1, 2. One of them has a dy dx, and the other one doesn't. Get everything with a dy dx onto one side of the equation, and everything without a dy dx on the other side. So I'm going to leave the 2y dy dx over here for a second. That's this term right here. And I'm going to subtract 2x from both sides. And now I'm going to divide both sides of the equation by 2y. So dy dx equals minus 2x all over 2y. Clearly the 2's cancel. So I'm just left with minus x over y. And there I am. I'm done. The upside of implicit differentiation is it's generally either easier or sometimes when isolating y is impossible, at least this is possible. The downside is your answer is going to have x's and y's in it. That's going to be okay. That's okay for us. So let's go back to our more difficult example now. Let's just do the same thing we did over here with that. We're going to need a bunch of our derivative rules here. We'll need the product rule and we'll need the chain rule. So if the question is, here's our function, and I ask you to find dy dx, find the derivative of that, all of that. Then what we're going to do is we're going to take the derivative of both sides with respect to x. X is going to be our independent variable. Y will be a function of x. Y will be dependent. We're going to go through term by term. We have 1, 2, 3, 4 terms on this side and 1 on that side. So the first term should be easy. That's just got x's in it. So derivative of x cubed, 3 times x to the 3 minus 1, 3 times x squared. That at this point should be easy for you. Now let's take a look at this. What we have here is a product. So product rule first times the derivative of the second. Derivative of y is just dy dx. Or you can think of it as 1 times dy dx, if you like, plus the derivative of the first, derivative of x squared is 2x, times the second exactly as it is. Product rule. So these two terms came from that one term, because we know we have a product there, we have to use the product rule. Product rule produces 2 terms. Does that make sense so far? Is there anything I can clarify anywhere? Okay, I'm going to assume no news is good news, but oh, thank you. So I got a thumbs up there, and a yes, another thumbs up, awesome. Okay, good, great. Okay, if there's any problem, unmute yourself and let me know. Let's go on to the third term now. Again, product rule. First times the derivative of the second. First is just x. Derivative of y squared. Again, we have that. We have a composition there. The inside function is y, and the outside function is something squared. So let's do the outside part. That 2 comes down. Y to the first power. And now multiply by the derivative of the inside part. Now we're not finished with this yet. That's just the first times the derivative of the second. Now we have to do plus the derivative of the first times the second. So plus derivative of x is just 1, which I don't have to write down, times the second exactly as it is. So if that looks confusing there, put the 1 in front of it. That was the derivative of the x. So this term gave us these two terms. Again, product rule and chain rule. Plus, oops, looks like that plus sign's in the exponent. Plus derivative of y cubed. If you could do the derivative of y squared over here, you could do the derivative of y cubed. Again, chain rule, you have an outside part and an inside part. Derivative of something cubed is 3 times that something squared. Now multiply by the derivative of the inside part, so put in the dy dx. So again, you can sort of think of it this way. Every time you take the derivative of a y, just put in a dy dx, which is the derivative of y. And basically what you're using is the chain rule. Equals the derivative of 15, which is 0. Derivative of any constant is 0. So the machinery of calculus is more or less finished at this point. All we have to do is get dy dx by itself. Now let's just take a look back and see what we got so far. We have 1, 2, 3, 4, 5, 6 terms. 3 of them have dy dx's in them, and the other 3 don't. Take the 3 that don't and push them all to the right side. So I'm going to leave this over here because it does have a dy dx, x squared dy dx. I'm going to leave this here plus x times 2y I can rewrite as 2xy dy dx. And I'm going to leave this one here because it still has a dy dx in it, plus 3y squared dy dx equals, now I'm going to subtract this from both sides, so minus 3x squared. I am going to subtract this from both sides, so minus 2xy. And I'm going to subtract this from both sides, minus y squared. So I've moved everything without a dy dx onto the right-hand side. I just left everything with the dy dx alone. Now, since everything on the left-hand side of the equation has a dy dx in it, I can just factor that out. That leaves me with an x squared plus 2xy plus 3y squared. And I'm not going to do anything right now with the right-hand side. Minus 3x squared minus 2xy minus y squared. And divide both sides by that. So minus 3x squared minus 2xy minus y squared on the top, all over x squared plus 2xy plus 3y squared. And there we go. We have dy dx all by itself. Our answer does have x's and y's in it, but that's okay. And resist the urge to try to cancel like one term on the bottom with one term on the top. Cancellation just doesn't work that way. So just make sure that you're careful with your algebra as you're looking at that. Does everybody get the process of implicit differentiation? Awesome. In that case, I will see you all on, what's today? On Friday. Take care, everyone.
Thank you.
My pleasure.
Have a good day.
You too.